Uh, so today we're gonna start section 15.4, which is about Green's theorem in the plane. So we know from 15.3 that f conservative if and only if the integral over any closed curve, f dot dr equal to 0 for all closed curve C. Now 15.4 is about what if f equal mn is not conservative. Very important that here we are talking about in the plane. Okay. The thing about in 3 dimension, this you will see it, this is the end of this chapter. Okay. So up to 15.4, so in section 15.4, we'll generalize the property, the loop property on the loop property into non-conservative field on 2 dimension. Okay. Well, if f is conservative, the integral over any loop is 0. If f is not conservative, the only way we know how to do it for right now is to use the definition that integral of f dot dr is mdx plus mdy, and f of r of t dot v of t dt. But the question is there another way to calculate this line integral that would make our life easier? So let's start with the motivation. Say I have a rectangle, a very small rectangle. So this is x, y. This is x plus delta x. And this is x, y plus delta y. And this is x plus delta x, y plus delta y. And this is my curve C. Okay. Let's call this L1, let's call this L2, let's call this L3, let's call this L4, and say I have a field F. Now integral over the rectangle of F, so the question is to estimate this, F dot TDS. Okay. Now I know that, so we know that here I have f is mn. So this is in 2 dimensions. Integral over the rectangle f dot t ds is equal integral over L1 f dot t ds plus integral over L2 f dot t ds plus integral over L3 f dot t ds plus integral over L4 f dot t ds. Okay. Now about L1. Yes, integral over L1 f dot t ds. This is equal. Now what is the tangent vector, the unit tangent vector to L1? So it's a straight line, so this is a tangent vector, and I want it unit, so this will be the vector I. So this will be integral over L1 of f dotted with I ds. Let's assume that delta x is very small, so that f is approximately a constant in I, so this is x plus delta x, y. As f is approximately a constant on each of the side, so this will be m1, because f is mn, times integral over L1 ds, which is the length of L1, and this is equal m1 delta x, and this is equal m of x, y delta x, approximately. Okay. Now what about L2? Now integral over L2 of f dot t ds, this is equal integral over L2 of f dotted. Now in this case, the unit tangent vector is upward. Yes, so this is the vector j. So this is f dot j ds But let's say f is a constant, so this will be n2, because f is mn, and mn.j is just n, integral over L2 ds, which is n2, the length of L2, which is delta y. So this is approximately equal to n of x plus delta x, comma, y, delta y. Now what about integral over L3 of f dot t ds? Is equal to integral over L3 of f dotted. Now let's look at the unit tangent vector. Now I'm going to the left. So this is the vector minus I. F dot minus I ds. Remember, t is always a unit vector. So this is approximately equal to m3 integral over L3 ds, and I have a minus. And this equal minus m3, the length of side L3, which is delta x. And this is approximately equal to m of x, y plus delta y times delta x. Still I have L4. What's integral over L4 of f dot t ds? It's equal to integral over L4 f dot. Now I'm going downward. So this is a vector minus j. This is a unit tangent vector to the line segment. Dotted minus j ds. So this is approximately equal minus n4 integral over L4 ds. And this is equal minus here. I have a minus that one drop. Minus n, well, minus n4 delta y. And this is approximately equal minus n of x, comma y, delta y. So let's add everything together. So we get that. Then integral over the rectangle of f dot t ds. This is equal integral over L1 and integral over L3. I will combine them. This will be m of xy minus m of xy plus delta y, both multiplied by delta x, plus n of x plus delta x, comma y, this one, minus n of xy delta y. Now, so this is approximately equal, definitely. So this is approximately equal. Now, what is m? So I will write this as minus m of xy plus delta y minus m of xy times delta x plus n of x plus delta x. So this is now equal to the previous one, minus n of xy delta y. Now this is approximately now minus. So here I'm fixing my x and I'm changing my y. So this is approximately the derivative of m with respect to y times the how much my y changed times delta y. And all this times delta x plus. What about here? I'm varying my x, here y, and I'm fixing my y. So this is approximately delta n over delta x times delta x delta y, and this is equal, so I got integral over the small rectangle f dot t ds, which is is equal n x minus my delta x delta y. So this is the circulation of f along the rectangle C is approximately nx minus my times what? Times this is the area of the rectangle. Do you agree? It's delta x times delta y. It's length times width. So I call this, so this is approximately now. So definition, given f equal mn, the scalar curve nx minus my, which is this quantity, it's called scalar curve, represents the circulation density of F denoted by the notation that's used in the book. I will not use it in general, but it's in the book, it's in the exercise, curl F dot K, and we'll explain maybe at the end, well, definitely we'll explain at the end of this, at the end of this chapter why it's called curl F dot K. Notice that this and x minus my does not depend on my curve, it only depends on F. And this is circulation, and this is counterclockwise circulation. And this is the area of the rectangle. It's very important here that it's counterclockwise. Okay. And this is nx minus my, and this is circulation per area, per unit area, which is the circulation density. Now, what if I have a larger rectangle? What if I cannot approximate this way? What if the rectangle is large so that the approximation does not work? I mean, I'm estimating delta x and delta y are very small, but what if they are not? So let's say I have a large rectangle and I want to calculate the circulation, let's call it C, the circulation over C of F dot T ds. Now, if it was a small enough rectangle, maybe I can use the thing above and x minus my delta x delta y, but this is not gonna work here because, I mean, it's not gonna, I mean, this is, let's say the rectangle is large enough so that I cannot do it this way. Even what I said above, this is approximation. I mean, I didn't prove it, okay? It's not, because, I mean, delta x, delta y, even if they are too small, they're never small enough to be able to calculate, to be able to, for this to be an identity. So it should be infinitesimal. So what I do is the following. I divide this rectangle into 4 pieces. And I start here. I calculate the line integral over the smaller blue rectangle. And then I calculate the line integral over the second integral. And then I calculate the line integral over the third line rectangle. And then I calculate the line integral over the fourth line integral. So notice that if I integrate over R1 plus the integral over R2, I have, when I integrate over this line, I have, this is going upward. When I calculate over R2, it's going downward. And you know, when you reverse the path, the line integral of a vector field becomes minus. So the line integral of R1 plus the line integral over R2 will become equal to the line integral over the whole thing here, correct? With this line cancelled. Now let's add the line integral over R3. So the line integral over R3 here, then this will cancel, because when I calculate R2, I have this is going this way, when I calculate R3, it's going this way. And similarly, when I calculate over R4, this line will cancel and this line will cancel. So what is the integral over R1 plus integral over R2 plus integral over R3 plus integral over R4? Which are the arrow that really survive? It's the arrow that are the boundary of my big rectangle, correct? So this is equal integral over R1 f dot t ds plus integral over R2 f dot t ds plus integral over R3 plus integral over R4 f dot t. But maybe these rectangles are not small enough to use the property that we learned from the previous, from above. I mean, maybe I cannot approximate as I did here. So what I do is I redivide this into 4 pieces. I redivide this into 4 pieces and divide this into 4 pieces, divide it into 4 pieces. And I keep doing this at every step. Okay, you can continue what I'm doing here. So what this is saying is, and maybe I have rectangles that are at the end of the day small enough, and then I will get, this will be integral to be summation of integral over small, very small rectangles f dot t ds, correct? Small rectangles. But let's say, let's keep doing this until the rectangles are very small enough. So this will be approximately summation over I of nx minus my delta x delta y. How to make this equal is by taking smaller and smaller and smaller rectangle, which means by letting the number of rectangles goes to infinity. So we get by, so this is like a Riemann sum here, integral over c of f dot t ds, again this is counterclockwise, is equal. Now this is here, when I let the number of samples goes into infinity, this is a double integral over r of nx minus my dx dy dx, so I will just write it dA. And this is Green's theorem. Okay. So in order to calculate the line integral over the boundary, I calculate the double integral, not of f of the scalar curl or the circulation density, over the interior or over the region enclosed by the rectangle. Now what if C is not a rectangle? This will be a bit more complicated, but I mean same formula. So let's say C is this way. Then what you really do, I mean the rigorous proof, but you have to divide this into rectangles again. This is not as simple here. The proof is a bit more complicated. But now I have these are not rectangles, so I redivide these into smaller rectangle. Now the upward are not rectangles, so you redo this. And then at the limit you get integral over c f dot t ds is equal double integral. So what's going on here is that the remaining things are not rectangles. So you redivide them into the rectangles, and this you let n goes to infinity. And with some strong theorem, I mean, you can do this, okay? But again, this is much more than the level of the course dA. Okay? So this is the motivation, and now the theorem. Now before saying the theorem, I need a definition. A simple closed curve that does not, well, what's that simply is a curve that doesn't self-intersect, well, except at the endpoint. I mean, it's closed, so it should intersect at the endpoint. Example, this is simple, but this is not simple. Why it's not simple? You have intersection here, okay? Now the theorem, and this is called tangential, well, Green's theorem in the plane, tangential form. Yes, before stating this, to justify one thing. So in order to calculate, let's say we have this case. I'm looking at this rectangle. Let's say I want to calculate the line integral over the rectangle explicitly. Then I use f dot v dt. In order for this integral to make sense, I only need f to be continuous here at the boundary. Okay? And then this will be completely fine. But when I calculate nx minus my r, where r is what is inside, then I need nx. It's not enough for f to be continuous at the boundary. I need nx minus my to be continuous in the interior of the rectangle, or in the region enclosed by the rectangle. So I need an additional condition. It's not enough for f to be continuous at the boundary of C or at C, I need nx and my to be continuous in the region enclosed by C, because this is nx minus my not at the boundary. Here R is the region enclosed by C. So now you have all the ingredients for the theorem. Let C be a piecewise smooth, simple, closed, right? Yeah, all this we're doing closed curve, and F equal Mn, a vector field, well, enclosing a region R. So I have a closed curve here, this is C and this is R. Now let F equal Mn be a vector field with M and N having continuous partial derivative of order 1 in open domain containing R, or R. So let's go a little bit further, and let's say this is D, and I have F is differentiable. Not differentiable. I have nx and my exists, and they are continuous. So F is differentiable, and the partial derivative of order 1 are continuous in R, and on C. You see, so we say we take a little bit room for the for technicality in the proof. I take a little bit more room than the closed set R with C. Then the counterclockwise, what if it was clockwise? Well, you put a minus. Circulation of F over C is integral over C of F dotted dr is equal to integral over C m dx minus n dy. So the total circulation is equal circulation density nx minus my times area, and we sum up over R. And this is Green's theorem. Now remark, if F is conservative and satisfying the condition above, then what? Then nx will be equal to my, and the right hand side will be 0 as expected, because we know that if a field is conservative, then the integral over any loop is 0. So this is Green's theorem is generalizing the loop property to more general field. If it's conservative, this gives me 0. If it's not conservative, then this gives me whatever the curve, whatever this integral is. Okay, I'll do 2 examples, and maybe 3 examples, and